Whenever two massive objects collide, they send out ripples in the fabric of space-time. These ripples are called the gravitational waves, and they serve as the signature of the merger that has occurred. Over the years, researchers have observed dozens of mergers of pairs of black holes and a couple of mergers of neutron star pairs. But for the first time, in June 2021, scientists caught a glimpse of a colossal merger of a black hole and a neutron star, taking place about 900 million light-years away from Earth, and that too, twice. The first merger involved a black hole about 9 times the mass of the Sun and a neutron star about 2 solar masses. 10 days later, the second collision was detected involving a black hole nearly 6 times the Sun's mass, devouring a neutron star of 1.5 solar masses. The observations further predicted that a merger between a black hole and a neutron star occurs once every month within 1 billion light-years of Earth. Although the collision observations have opened up many new doors of impending discoveries, LIGO and Virgo are not enough to entangle all the cosmic mysteries. So keeping this in mind, twin LIGO detectors, Virgo and Cagra, are all undergoing preparations for another set of observations scheduled to begin next summer. To the best of our knowledge, everything we see around is governed by 4 fundamental forces: gravity, electromagnetic force, the strong nuclear force, and the weak nuclear force. The theory that combines all these forces, except gravity, is the standard model of physics. Although experiments conducted over several decades have verified the standard model, it is not complete. For example, it does not unify gravity with the other 3 forces, and does not explain dark matter and dark energy that make up 96% of the observable universe. That's why physicists have been looking for a 5th force for decades, and one place to find them is in the decay of bottom or beauty quarks. It's an unstable particle and lives for just 1.5 trillionths of a second before decaying into other particles. When a beauty quark decays, it transforms into a set of lighter particles, such as electrons, through the influence of the weak force. So, one of the ways the new force of nature might make itself known to us is by subtly changing how often beauty quarks decay into different types of particles. According to the standard model, a beauty quark should not discriminate between an electron and a muon while decaying. A muon is a carbon copy of an electron, except that it is 200 times heavier. The rate at which the beauty quark decays into a muon must be equal to the electron. But in March 2021, the researchers found that the muon decay was only happening about 85% as often as the electron decay. Nature seems to be preferring one decay channel over the other, a violation of the law of lepton universality. Physicists believe an unknown force must be breaking the law of lepton universality. We might be on the brink of a significant breakthrough in physics, but more data is required to confirm the existence of this new force. Despite being the farthest spacecraft from Earth, Voyager 1 feeds us interesting deep space information, and this is exactly what it did in May 2021. The farthest human-made object detected an unexpectedly steady hum of plasma waves in interstellar space. This hum was persistent, long-lasting, with a low frequency drowning away at approximately 3 kHz. Plasma is a hot, diffused, and ionized gas composed of electrons that have been stripped away from their atoms, also known to be present in the interstellar medium. The movement of electrons in plasma leads to thermally excited plasma oscillations, or quasi-thermal noise. Voyager 1 is well equipped to measure these plasma vibrations in the interstellar medium thanks to its inboard plasma wave system. Since 2012, Voyager 1 had detected about 8 distinct plasma oscillation events, which ranged in length from a couple of days to a full year. These events were mainly caused by instabilities in the motions of electrons as they interacted with shock waves generated by the Sun. However, in 2017, Voyager 1 began to detect a weak, steady, and persistent plasma signature outside of the energetic events. The newly detected signal was narrower than the plasma oscillation events and held itself steady at about 3 kHz, and bandwidth restricted to 40 Hz. Moreover, this feeble signal persisted for nearly 3 years, the longest continuous plasma signal recorded by Voyager 1 so far. In the last 3 years, Voyager 1 traveled a distance of about 10 astronomical units, which is roughly 930 million miles. But the signal remained the same. Since the measured signal was just above the noise threshold of the Voyager 1 plasma wave system instrument, researchers did not expect to find anything like it. Although the signal is quiet, it's stronger than scientists previously thought, and its detection has pushed Voyager 1's limits of what it was earlier thought capable of doing. Moreover, the persistence of the signal suggested that Voyager may continue to detect it in the future as well. Wormholes are portals in space-time that serve as shortcuts for long interstellar travels. Having its origin in Einstein's theory of general relativity, a wormhole is a highly curved region of space-time that connects two extremely distant points in space, just like a tunnel. However, these exotic structures are theoretical and haven't been directly observed in nature. Moreover, mathematics suggests that such wormholes would be extremely unstable, and if anything tries to pass through them, they would immediately collapse. Eventually, the matter passing through it would disappear, and the connection that the wormhole provided to other places in the universe would be cut off forever. Previous models suggested that the only way to keep a wormhole open is with an exotic form of matter with a negative mass. But in 2021, 2 different theories were proposed, according to which time travel could actually be possible via wormholes, and that too for normal matter, provided we follow some constraints. So, in the first approach, published in March 2021, researchers chose a comparatively simple semi-classical approach. They combined the elements of relativity with quantum mechanics and classical electrodynamics. They found that if we included the Dirac equation into our mathematics, it would permit the existence of a wormhole traversable by matter such as electrons, provided the ratio between the electric charge and the mass of the wormhole exceeded a certain limit. According to this theory, even electromagnetic waves could also traverse the tiny tunnels in space-time. Then, in the second approach, published in September 2021, scientists employed a tweaked form of gravity called generalized hybrid metric Palatini gravity to make wormholes traversable. Although this theory is built on Einstein's general theory of relativity, it allows more flexibility in relationships between matter and energy and space and time. It was found that layering the entrances to the wormholes with double-thin shells of regular matter would make the wormhole traversable without the use of any exotic matter and negative energy. Although both approaches are still only in papers, the researchers aim to test their theories experimentally in the future. And if proved true, these theories wouldn't just make our sci-fi dreams come true, but also challenge our current understanding of the universe. In 1971, Stephen Hawking gave one of his theorems according to which a black hole couldn't decrease in size over time. This theorem, known as the black hole area theorem, works on a similar thermodynamic principle that entropy cannot decrease over time. After 41 years of being proposed, in July 2021, scientists have finally proved Stephen Hawking's black hole area law by analyzing the gravitational waves produced by two black holes 1.3 billion years ago. If Hawking's area theorem holds, then the horizon area of the new black hole formed due to the merger should not have been smaller than the total horizon area of its parent black holes. So, to conclude this, researchers split the gravitational wave data registered by LIGO into two categories, before and after the merger. Later, they used both the measurements to calculate the surface areas of the black holes in each category, and found that the total surface area of the combined black hole was greater than the sum of the two smaller black holes. This means that the total event horizon area did not decrease after the merger. This result was reported with 95% confidence, thereby solidifying Hawking's area law. However, despite being a breakthrough, this confirmation oddly contradicts another crucial theory of Hawking radiation, according to which black holes spontaneously emit thermal radiation over time. Keeping this in mind, the team aims to test future gravitational wave signals to see if they might further confirm Hawking's theorem or sow the seeds of new physics. If you're interested in studying astrophysics at home, make sure to check out our Basics of Astrophysics series, the link to which is given in the description. This series explains everything at the most fundamental level, from the EM spectrum to telescopes, and from the birth of stars to the formation of black holes and galaxies.